as the condition suggests, the wave functions are valid in the region x less than x1. That means far away from the classical turning point at the left side, and also it is valid in the intermediate region, which is classically allowed region, but away from both x1 and x2. This situation suggests that. Okay. Similarly, for region 3 also, the wave function psi3 is valid whenever the domain is very far away from the classical turning point x2. So it is okay. But if we have a valid physical system, we have a uh, we have a valid physical system, and we must infer the wave function should be continuous, right? The wave function should be continuous, right? The wave function should be continuous everywhere. Okay, may it be classical turning points, but whatever it may be, the wave function must be continuous at every point within the region. So we have to make some connections between these approximated scheme. Okay, we have to make the connections between psi1 and psi2, and also psi2 and psi3. But of course, we can't write these wave functions from the Wkb approximation, because it is clear Wkb approximation is only valid for slowly varying potential. But as the prescription suggests, near the classical turning points, the potential will blow up. Okay, the potential will yield some infinite value. So there, the potential will not be slowly varying. So we have to make some other consideration or some other approach to find the connecting wave functions. I am giving the nomenclature connecting wave function. What do you mean by connecting wave functions? Which makes the connections between these Wkb approximated wave function. I am giving the nomenclature that they are connecting wave functions. Okay. So we are in search for connecting wave. So in order to do that, suppose at first I am aiming to find the connection between psi2 and psi3. That means near about x2. So, near about x2, the right classical turning point. Okay. So here, suppose you have the potential Vx, and you have to find the nature of the variation of Vx around x2. Forget about the whole potential or the nature of the whole potential. Just try to find the variation or nature of potential Vx near about x2. So here you can write from Taylor series expansion. This is Taylor series expansion Vx2, and then x minus x2 del v by del x at x2, and the higher order of x minus x2. Okay, the higher order is generally I am denoting as theta of x minus. And as the prescription suggests, I am telling about the nature of the potential, the region nearing x2. That means we choose x nearing x2, both plus minus. That means suppose this is x2, I am trying to locate ourselves within this region. So here x is very near to x2 from both left side as well as from right side. So x minus x2 is very small. So you can neglect the higher order terms and just you can put or you can keep the first order term. So this is the approximated potential about x2. Okay. Now you can write the Schrodinger equation. It's a one-dimensional potential I am choosing. So 8 h cut square minus h cut square by twice m del 2 psi by del x2 plus vx psi x. Psi is basically function of x. Time independent Schrodinger equation E of psi x. Okay, E of psi x. Now look at here. Suppose this term is a constant, because after derivative or after making the differentiation, you can put the value of x2. So basically it will be a constant. Suppose this is f. Okay, in many quantum mechanics book it is taken as f. So I need not change this convention. You can take anything, but suppose it's f. Okay. Now v of x2. What is v of x2? So it is very clear what is the definition of classical turning point. At the classical turning point, the momentum is zero, right? At the classical turning point, momentum is zero. And you know momentum px is equal to root over twice m e minus vx. So at classical turning point, suppose p of x2, v of x2, it is zero. So from here you can write vx equals to e. Similarly, v of x1 also. V of x1 also e. So you can put v of x2 is equal to e. So now you can write h cut square by twice m del 2 psi by del x2 plus you can write this is e plus f of x minus x2. You can negate the higher order terms with psi x equals to e of psi x. And of course, clearly you can cancel out these terms from the both sides. E of psi x and e of psi x. Okay? It's clear? Now, in this slide, I'll write one more sentence, one more equation. Then you can write del 2 psi by del x2 minus twice m f by h cut square. Am I okay with this? Okay. X minus x2 is equal to 0. Psi is very much a function of x. So I am dropping this dependence again and again. Okay. So this one. So now you have to solve this equation. This very Schrodinger equation. Okay, but it looks very complicated because it contains some extra constant terms. These are constant, but to make the smooth procedure of solution, you have to make the coordinate transformation. Okay, to normalize this all of these constants to be in a very suitable way. Okay, so here I make a coordinate transformation like that. Suppose x goes to y, and y is, suppose I am writing, let it be beta. Okay, beta x minus x2. It's a linear transformation. Okay, y to x, it's very linear transformation, just like Lorentz transformation. Okay, x prime equals to gamma into x minus vt. Okay, x prime equal to x minus vt by root over 1 minus v square by c square. Such type of equation, such type of transformation. Okay, so y equal to that, but one difference is there t was not constant, but here t x2 is a constant number. Just the value of x2 is constant. It's somehow different, but somehow similar also. Okay, so that is our coordinate transformation. Okay, now you know del psi by del x. Okay, del psi by del x. So del psi by del x will be basically del psi by del y into del y by del x, right? So del y by del x means beta. This is beta del psi by del y, and also you have del 2 psi del x2. You have to make another similar type of derivative. So you will find beta square del 2 psi by del y2. Okay, now you have to put this transformation in the to find the effect of this transformation in this equation. You have to put all of these. So you can write beta square del 2 psi by del y2 minus twice m f by h cut square with x1 minus x2 means y by beta, okay, is equal to 0. So here I am writing directly, so this is beta cube. Can you write it? Okay, of course I am missing one, which is psi. So now we have such transformation, and this beta was actually taken as a free parameter. What do you mean by free parameter? Can you answer it? What is free parameter? Free parameter is basically a constant, but you can take any value of that constant. So we can take the suitable value of beta. It's in our hand. Okay. So we shall take the value of beta in a suitable way, such that the equation may be normalized, or the equation may be very looks very easy. So suppose I am taking the value of beta in such a way so that the whole thing have the value 1. This whole thing have the value 1. Okay, so suppose 2. So you can write beta is equal to twice ma by h cut square whole to the power 1/3. Okay, this one. Okay. So I am taking the value of this free parameter beta in that way. So the equation now looks very looks comparatively easy, which is del 2 psi del y2 minus y psi is equal to 0. Now this equation looks very trivial, like a harmonic oscillator type equation, but actually that's not, because this y is not a constant. If instead of y there may be some constant term, then you can write it's a harmonic oscillator equation, but it is not the harmonic oscillator equation. Okay. So you have to solve this equation, and the solution of this equation yield a very special function, and this y is proportional to the psi of y is proportional to some special function called ARE function, ARE function of y. Okay, so ARE function of y, and this ARE function of y, can you say the integral form of this?
सर एआरई फंक्शन बोलते
Like Legendre function, Legendre polynomial, like Hermite polynomial, like Bessel function, it's a special function. Okay, so you have already studied different special functions. It's another special function. Okay. Another special functions like that is Bayari function. It is ARE function, and similar kind of, that means the second kind of ARE function, it's called the Bayari function, like Bessel function. Bessel function of first kind J, and Bessel function of second kind eta. Eta is called the Newman function. In the similar fashion, this is ARE function of first kind, and the second kind of ARE function is Bayari function basically. So this equation is like ARE differential equation, ARE differential equation. So the solution will be like that. And the integral form of ARE function is, can you speak? It is 1 by pi integration from 0 to infinite cos of No, t cube by 3 plus ty dt. This is the integral form of Airy function. You have to remember this form. Okay. So accumulating all of these, okay, look at this very carefully. The form of Airy function in integral way is like that. Every special function has some integral form, like Legendre, like Hermite, like Bessel. It's another special function, and it has the integral form like that way. So the solution psi of y, I am writing with some constant, uh, because instead of proportional to symbol I am using equal. Then you have some constant a prime with Airy function. That means yes, integration from 0 to infinite cos of t cube by 3 plus yt dt. Clear till now? Now we have the solutions, the connection wave functions near about x2. Okay, you can transform it in terms of x, because this is the transformed coordinate. You can make the reverse transformation by putting the value of y. You can find it, but now you have another responsibility. Okay, you have already found the connecting wave functions. Already you have the approximated wave function, but you have another responsibility to make them connected, make the connection formula between. Okay, so uh, in order to do that, you have to find the value of this wave function psi in the in that approach. Okay, that means in that limit. Okay, you have to find the connection formula or connected wave function uh, in that limit. That means that limit x greater than x2 as well as x less than x2, because you have to make the connection between them. And the region starts from here. Normally the region is differentiated at the walls. Suppose you have two regions, like that. Suppose this is two region 1 and region 2. So this is wave function 1, suppose psi 1, and this is wave function 2 psi 2, and you can generally connect them at the boundary. But here the scenario is slightly different, because the uh, region does not start from here. The region starts way from this classical turning point. So in order to make them connected, uh, suppose I try to make you understand. Suppose this is x2. Okay, this is x2, suppose. So this is x2 point, and the Wkb psi 2, this is Wkb psi 2. Suppose I am writing psi 2 for Wkb is here, and psi 3 of Wkb is here, and this is the connection. This is the connection of psi, connecting psi. So you have to find the value of psi at that limit, and you have to find the value of psi at the limit. Then you can make them connected. Okay, so this is the difference between other formulas or other methodology and the WKB connections. So you have to find the connection between psi 1 psi 2, sorry. না না না, সাইটা এর কাছে, এই কাছাকাছি রিজিয়ন আছে। কন্টিনিউয়াস করতে চাইছি, বাট এরা কন্টিনিউয়াস নয়। ওকে, সো you have to find the value of this one, that means this psi at that limit and at that left-handed limit and right-handed. And fortunately, you have the form of Airy function, um, the form of Airy function like that. So ai of y is equal to 1 by root over of pi mod of y whole to the power 1 by 4, and this is suppose e to the power 1 by e to the power integration. Okay, the value is actually oh e to the power 2/3 minus y whole to the power 3 by 2 plus uh, sorry, the function, the value of Airy function is sine of, this is 2/3 minus of 3 by 2 plus pi by 4 when y less than 0. Okay, and 1 by 2 root over pi y to the power 1 by 4, not mod uh, e to the power 2 by 3 y to the power minus 2 by 3 to the power 3 by 2 when y greater than 0. Okay, this is value of Airy function at that limit. So y less than 0 means x less than x2, and y greater than 0, that means x greater than x2. So in our desired limit, we have already found these values. Okay, so also then you can write the wave functions. So psi of y, so I am writing this is suppose psi c, that means connecting wave function. Okay, psi c or connecting wave function is basically a prime by root over pi mod of y whole to the power 1 by 4. Okay, so this is sine 2/3 minus y whole to the power 3 by 2, then plus pi by 4 when y less than 0, sorry, y less than 0. Okay, and equals to root pi 2 root pi y to the power 1 by 4 e to the power minus 2 by 3 y to the power 3 by 2. No, when y greater than 0. Okay, so this is our connecting wave function, and the form of this one in the desired limit, that means in the limit of Wkb approximated scheme wave function. Okay, now you can connect them. So before connecting them, you have to find these values, the value of y to the power 1 by 4 and this one in terms of our known parameter. Our known parameter is the momentum. Our known parameter is suppose the y is not our known parameter. Okay, so you have to make the transformation. So in order to do that, at first you have px square. You know the value of px square, which is twice m e minus vx, right? Okay, twice m e minus vx. Now this is twice m e minus f this one. So this is minus twice m f x minus x naught. What is x minus x naught? X minus x naught means y by beta. Okay, and what is beta? What is the value of beta? Twice mf 1/3. Okay, so now you can simplify also. Px square is equal to uh, f to the power 2/3 twice m f to the power 2/3 and h cut square also. So h twice m f h cut, right? So minus twice m f h cut whole to the power 2/3 into y. Okay, so suppose this one. Okay, so what is px now? Twice m f h cut whole to the power 1/3 root over minus. Okay, hmm? Now this one. Suppose this is 1 by h cut from x1 to x. Okay, 1 by h cut x1 to x px dx. Okay, 1 by h cut like that px dx. So you have to put the value of dx here. So dx is equal to dy by beta, right? Dx is equal to dy by beta, and you can put the value of beta also. It's very easy. So 1 by h cut from x1 to x2. What is px? Px means twice m f h cut whole to the power 1/3 root over minus y, and by beta means twice m f by h cut whole to the power 1/3 into dy. So basically twice mf twice mf twice mf will be cancelled out, then h cut will be over there, so h cut square whole to the power 2/3. Oh sorry, this one actually h cut square, this one was h cut square. So h cut to the power 2/3 and h cut to the power 1/3, so it will yield h cut. So this one, this one, this one, so this is very well set up. Yeah, this is very well set up, and it will normalize to suppose equals to integration root over minus y dy, and the limit of y, because y is equal to beta into so whenever beta equal to sorry it should be x2. Okay, for because I am going to find x2 near about x2. So whenever beta is whenever x equal to x2, for x equal to x2, y will be 0. So this will be 0 to y. Okay, the limit will be sorry. So this is from x2 to x. So this is like that. So this is plus y. Now you can put suppose minus y equal to z. Okay. So it will be minus dz. So minus root z dz from this will be 0 to minus z. Okay, and this should be minus 2 by third, right? Minus 2 by third z to the power then minus z to the power 3 by 2. Okay, minus z to the power 3 by 2, and then it will be plus. Okay, so this is sorry, no, sorry, this should be minus again. So minus z, so z equal to minus y, so this is minus 2 by 3 z to the y to the power 3 by 2. Okay, so the limit is like that. So from here, if you look at here, so this was actually on the exponent of the exponent on the Airy function. Okay, this was actually was in the exponent of the Airy function. So you can replace this one in terms of px in the expression of Airy function. So so here you can write psi x is equal to, so you can also here change the, you can put the value of px, so you will find suppose another a constant, suppose I am writing this, suppose a. Okay, I have changed from a prime to a because some constants will be multiplied with a prime. So with the mod of px, okay, uh, mod of px with sine, it will be 1 by h cut integration from uh, x to x2. Okay, x to x2. X less than x1, x less than x2, then it will be mod of px dx plus pi by 4 when it is x less than x2. And similarly this was a by 2 because one extra half was there, so this is root over of px e to the power minus 1 by h cut integration from x2 to x, okay, px dx when x greater than x2. So this was our connecting wave function in a complete way. So this was complete way, this is a complete wave connecting wave function in a completed way in terms of x we have found. Okay, now you can compare it with the, after putting this one you have found this, এটাই তো বসালাম, y জায়গায় তো এটা বসালাম, এটা ছিল y, এয়ারি ফাংশন, এখানে এয়ারি ফাংশন কি এটা ছিল না, তার জায়গায় তো এটা পুট করব। ওকে, now if you compare it with psi 2 wkb, okay, so sorry, or wkb, so the value of psi 2 wkb was similar, the value of psi 2 wkb was similar in that way, but only difference was the constant. So there it was c2, right? So c2 will be equals to a, so you can check that for this. This psi 1, this is psi 2. Okay, c2 by root px in a similar way, and alpha will be equal to pi by 4. Okay, and from here you will find alpha equals to pi by 4. Alpha equals to pi by 4. And also if you compare it with psi Wkb3, so psi Wkb3 means in the region x greater than x2. So you will find a by root 2 equal to c3. Okay, a by root 2 sorry, a by 2 equal to c3. So a equal to c2 equal to 2c3. Okay, so c2 equal to 2c3. So this was the connection, and from this connection we will find the unknown constants from Wkb approximated wave function, which is alpha. Alpha is equal to pi by 4. And you may drive the similar operation for psi1 and psi2. For connecting psi1 and psi2, you have to make the Taylor series expansion of the potential near about x equal to x1. Okay, near about x equal to x1, and you will find the connecting wave function will be like 1 by 2 root over of pi e to the power 1 by h cut from x1 to x. Okay, it will be from x1 to x mod of px dx when x less than x1. Okay, and sorry, so, okay, all right, it is half, and then only the difference is it should be mod of px. Okay, I'll skip all of these calculations, and the calculations will be similar for psi 2 psi 3 and psi 1 psi 2, because the equation of Schrodinger equation will be same, Airy differential equation. As the equation was similar, Airy differential equation, the solutions and the whole proceeding will be repeated, just these numbers will be changed. And similarly it will be so you can write this is suppose b. Okay, this is b. You have to put constant, the constant is b. There the constant was a, but I am writing it's different, it's b. So it's b. So b by root px e to the power minus, sorry, it will be in terms of sine. Okay, so this is sine 1 by h cut integration from x1 to x. Okay, px, it should be px, and dx plus pi by 4 when x greater than x2. Similar way, you can connect the psi 1 Wkb. Sorry, it should be x1. Okay, thank you. It is x1, classical turning point on the left hand side. So now you can connect it, this psi c, you can connect it psi 1 Wkb. Okay, at x less than x1, then you will find b by 2 equal to c1, right? B by 2 equal to c1, and psi 2 Wkb with x greater than x1, and there we will find b equal to c2 and alpha equals to pi by 4 again. Okay, so we have the connection between psi 1 and psi 2 and psi 2 and psi 3. Now you can connect all of these. So if you compare, okay, I have to take new slide. So if you compare the psi2 from left connection, psi2 from left connection was, what was the value? Psi2 from left connection, it was psi2 from left connection was b as b by root px sine 1 by h cut integration px dx plus pi by 4, right? And psi2 from right connection, okay, can you relate this one? Psi2 from left connection, that means at the final, sorry, this was the new slide. Okay, in the previous slide, psi2 from the left connection was like that. That means connecting from psi1 to psi2. And psi2 from right connection, that means connection between psi2 and psi3, will, you would find a by root over px. Okay, a by root over px sine of 1 by h cut integration px dx plus pi by 4. Of course, I have missed the limit. The limit was from x1 to x, and it was from x to x2. Okay, so psi2 from left connection, that means near about x1, and psi2 from right connection connecting near x2. The form was like that. Okay, suppose the whole thing is, suppose theta 1. This is suppose theta 1. This is the argument of sine. So this is suppose theta 1, and the argument of this one is theta 2. Okay, so now you can equate them. You can equate the both side too. After equating the two forms of psi2s, you have, this one will be cancelled out. You will find b sine theta 1 equals to a sine theta 2, right? Okay, b sine theta 1 is equal to a sine theta 2. Okay, now what is the outcome of this equation? It will yield, this equation will yield theta 1 plus theta 2 is equal to n plus 1 pi. Then you can write b equals to minus 1 whole to the power 1 n into a. So the solution of this equation will yield this one. And now you can put the value of theta 1 and theta 2. Okay, you can put the value of theta 1 and theta 2. So theta 1 is integration from x1 to x, sorry, px dx, and theta 2 is from x to x2 px dx plus pi by 4 and pi by 4. So pi by 2 equals to n plus 1 pi. Clear? Now this one, you can write integration from x1 to x2 px dx equal to n plus 1 minus half of pi, because pi by 2 can be cancelled out from the both sides. Okay, so you can write integration from x1 to x2 px dx equals to n plus half into uh, h by 2. H cut means h by 2 pi. So pi will be cancelled out. So this is h by 2. Okay, so this is the equation. Okay, now suppose a system has a classically allowed region, and the region is from x1 to x2. So if you make the h space, if you want to make the fetch space, and fetch space is only applicable under classically allowed region. You can draw the phase space in classically forbidden region. Why? Why? One open question for all of you. Why the phase space is not allowed in classically forbidden region? It's very simple. Momentum is imaginary. In classically forbidden region, momentum is imaginary. So you can draw the phase space there. Okay. So if you want to make the phase space, then you have to make within the classically allowed region. That means from x1 to x2. So the phase space volume will be integration px dx. That means from x1 to x2 and then from x2 to x1, which is equal to 2 of x1 to x2 px dx. So it is n plus half into h. So this is Sommerfeld quantization rule. This equation is called the Sommerfeld quantization. From x1 to x2 and x2 to x1, the closed path integration. For closed path integration, this is the total phase space volume or phase space area, whatever you can say. It is equal to that Sommerfeld quantization. Okay, so okay, so you can apply this one for the known potential. So suppose it is a homework for you. Vx equals to half of m omega square x square. What is the potential? What is the system corresponding to this potential? It is harmonic oscillator. So can you check this one for harmonic oscillator? Okay, you can put this one here and you will find the outcomes. And can you check the homework for you? Check whether it works with HO or not. This is homework for you. Okay. Now, the crucial application of WKB, the crucial application was not for this one because it can be solvable directly. The harmonic oscillator is can be directly solved, but the crucial application of WKB was different. Okay, the crucial application is suppose you have the potential like that Vx equal to half of m omega square x square for x greater or equal to 0. Okay, and infinity for x less than 0. So this is like that harmonic oscillator with one rigid walls. So these rigid walls actually uh, sealed the one classical turning point. Harmonic oscillator has two classical turning point. It is x2 and this is x1, but this rigid wall will alleviate the first one. So here the wave function will be 0. Okay, here the wave function will be 0. So then the connection relation will be changed. So from the left hand connection, from left hand connection, alpha will be 0 now. From left hand connection, alpha will be 0 because the wave function will be destroyed at the residuals. The wave function will go to 0 here. So it will not reach to the classical turning point. So you need not require to connect the left sided WKB approximated wave function. So from the boundary condition you will have alpha equals to 0. Okay, you will have alpha equals to 0. But from right hand from a right hand connection, alpha will be pi by 4. Okay, then the similar kind of condition will arise, which is suppose b sin theta 1 equal to a sin theta 2, but here theta 1 is equal to only that one, x1 to x dx dx plus 0, alpha is 0, and theta 2 is equal to 1 by h cut from x2 x2 dx dx plus pi by 4, because here alpha is pi by 4. Now from here you can write theta 1 plus theta 2 equals to n plus 1 pi. Okay. And after putting these values, you will find 1 by h cut from x1 to x2 dx dx is equal to n plus 1 minus 1 by 4 pi, right? Minus pi by 4. So this is n plus 3 by 4 pi. Okay. So integration from x1 to x2 dx, it will be n plus 1 into n plus 3 pi by 4, 3 by 4 into h by 2. So the whole fetch, sorry, px dx, whole fetch space volume will be n plus 3 by 4 into h. H. Okay. Okay. Now next one. Suppose the system with two residuals. This is one residual. This is another residual. The potential is embedded within the. That means yes. That means we have to neglect both the connection relation. Okay. Both of these will not reach up to the left-sided and right-sided Wkb approximated wave function. So effectively, you will find, what will you find? Here also alpha equals to 0 and here also alpha equal to 0. So you can write, I am skipping some steps. You will find 1 by h cut from x1 to x2 dx dx is equal to n plus 1 pi, and integration px dx integration px dx, it will be n plus 1 into h. So this is for the situation where potential is embedded within two residuals. Okay. This is for one residual, and without any residual, the condition is trivial, which is like that. Which is, sorry, this one. So without any residual, that means with no residual, the quantization condition is like that. With for one residual means the left hand connection will yield alpha equal to 0, the right hand connection will yield alpha equal to pi by 4. So effectively you have this one. Effectively you have this one. Okay. Now for two residuals, it will make some difference, and it is like that. Okay. So this is the Wkb approximation scheme. Oh, sorry. It should be only h. It's only h. Okay. Also, one more thing. You can write n equals to n is also. Okay, because n is integer, n plus 1 also integer. You can skip this one. But in general you can write this Sommerfeld approximation. Okay, so this is WKB approximation. ঠিক আছে, তাহলে পরের দিন আমরা এখান থেকে কিছু নিউমারিক্যালস করব। জেটলির বই থেকে আমরা প্রেফার করব অঙ্কগুলো করতে, কারণ ওগুলো থেকে এক্সামে আসে। ঠিক আছে, তো কোনো কোশ্চেন আছে তোমাদের?